let's say you want to solve a problem that involves Newton's laws or some sort of forces acting on an object. And let's say that object is a car. We know that cars have four wheels, they're very heavy, their mass may not be distributed evenly. You have the engine at the front that might make it heavier than an empty trunk on the back. So overall, the mass might not be evenly distributed, especially if there are also passengers sitting in that car. And that might make you think that, oh, this problem involving forces is really difficult to solve because how do I find out how the mass of every single passenger or every single part of the car is distributed? But generally, when we're solving problems involving forces and Newton's laws, we think about the entire object as a single system. So we have a car over here, but honestly, when we're solving problems, we usually just look at the car as, say, a box, a simplified shape of a box, where we only consider the entire mass of the car as uniformly distributed over the entire object. And if we can simplify it to a box, then at the end of the day, it's really the same thing as saying there is a specific point at the ideally center of mass of the car where all of the mass is concentrated at that singular point. So we can replace this car with a dot that represents the car. So this represents our car. And it no longer has the complicated shape or the complicated mass distributions that we were working with earlier. And now it's easier for us to solve these force problems because we can draw what is known as a free body diagram. A free body diagram. And a free body diagram will basically allow us to visualize the forces, the different components of the forces that are acting on a body. And generally, there are a couple of rules when it comes to drawing free body diagrams. First of all, the forces should always be starting from the object or originating at the object. So if I have a force of gravity here, this is the force of gravity, they should always be pointing in the direction that the force is acting on. So the force of gravity is acting downwards in this case. And usually before you start drawing any forces, it's always good to define like a reference frame or reference coordinate system. And we're going to define this as the positive x and this as the positive y direction. And the forces, again, should always be originating from the object itself. So if I have the force of gravity here, it should be starting from the dot and pointing downwards in the direction that the force of gravity is acting. It shouldn't be starting here, for example. It shouldn't be starting here. It should be starting at the dot. Similarly, if you have the normal force, you would be pointing up against the gravity if the car was on a road, say. And now let us imagine that we have that same car, but there is another object on it, say a person. So first you have the force of gravity from the car itself, and then there is a second force of gravity that acts on the person. And this person, in reaction to that force, the car must exert a certain force back on that person, and the person exerts a force on this car. So the person will exert a force on the car, like so, person on car. And notice how even though we have two forces, they're both starting from the point, which is the car. And in that case, the normal force from the ground on the car would be greater than the force of gravity on the car itself because we have this extra component from the person that we have to balance out with the normal force. So this is the new normal force. And also here comes another point of free body diagrams. The magnitude or the relative magnitudes of the arrows should be related to the relative magnitudes of the forces themselves. So here we can see that we would assume or expect that the force of gravity on a car would be greater than the force of gravity on a person. So the arrow for the car force of gravity is longer than that for the person. And now looking at the normal force, we see that the normal force is greater than both of these arrows, and it is equal actually to the sum of their lengths. So if we were to move the force of gravity on the person down and add it head to tail vector addition wise, we would get something like this. And notice how the length of the normal force approximately balances out the length of these two arrows added together. So we can also work in the x direction if there is, say, a force of friction acting on the car to the right. And we would simply draw it in the x-axis direction. So that is how you can use free body diagrams to solve and simplify problems and visualize them before you actually get on into the nitty-gritty math and equations. I hope you guys learned something new. Please come back next week for a new lecture on forces. Hope to see you soon.